Good evening once again, everyone. 8 people are now known dead this evening following the massive eruption of Mount St Helens early today. Geologists say this is by far the strongest eruption in the latest series, and it continues tonight. Channel 2's Essex Porter has the story.
Beneath the rugged forested slopes of the Pacific Northwest, the ground has never been entirely still. Even in moments of apparent calm, the Earth's crust here is alive with slow, hidden movement, ancient forces working far below the surface. Now, geologists have announced a striking development. A secondary magma plume has been tracked expanding to the northeast of Mount St Helens. This revelation has captured intense attention not only because of the volcano's dramatic past, but because of what such a plume represents in terms of geological activity, deep crustal processes, and the potential for future volcanic changes in the region. Before we start, smash the like and subscribe buttons for more updates. Mount St Helens itself is no stranger to scrutiny. Since its catastrophic 1980 eruption, it has been the subject of one of the most comprehensive volcanic monitoring programs in the world. But what geologists are now detecting lies not directly beneath the volcano's central vent. It is offset, forming a new and distinct zone of magmatic upwelling that appears to be moving in a northeast direction. This is a critical distinction. A plume is not a shallow pocket of molten rock. It is a focused column of heat and partially molten material rising from deep within the mantle or lower crust. When such a plume begins to shift, it signals a redistribution of magma and heat energy that can have wide-reaching geological consequences. The detection of this secondary plume was the result of years of subterranean imaging work, using seismic tomography, GPS deformation tracking, and magnetotelluric surveys. In essence, scientists have been taking repeated X-rays of the region's underground structure, watching for subtle changes in density and conductivity that can indicate molten rock moving through the crust. Over the past 2 years, their datasets began to reveal something unexpected: a high-temperature anomaly slowly intensifying, positioned several miles northeast of the main volcanic edifice. At first, the anomaly appeared modest, but by the latest round of measurements, the feature had grown both in size and thermal output, suggesting that magma is actively intruding into new rock layers in that direction. What makes this development so compelling is the nature of the Cascade Range's volcanic system. Mount St Helens is already the most active volcano in the range, but it sits within a larger network of magma sources, faults, and deep structural weaknesses. Magma plumes do not move randomly. They follow zones of least resistance, exploiting fractures, weaker rock formations, and pre-existing volcanic pathways. The northeastward trend suggests that the plume is finding such a path, potentially feeding an area of the crust that has not been as volcanically active in recent history. This raises intriguing questions about whether new surface vents could eventually form away from the main cone, or if existing minor fissures could become more significant. The precise dynamics of a secondary magma plume in this region are complex. Unlike a mantle plume that rises vertically from great depth, a plume feeding Mount St Helens is believed to originate from a magma reservoir that is itself supplied by subduction-related melting. The oceanic Juan de Fuca plate is sliding beneath the North American plate here, and water-rich sediments carried into the mantle trigger partial melting. This molten material gathers into reservoirs and can feed multiple volcanic features over time. The appearance of a new plume extending northeast could mean that magma is being diverted into a branching system rather than funneling solely toward the central magma chamber beneath the volcano. Tracking the expansion of such a plume requires more than just mapping its current boundaries. Scientists also analyze the seismic events that accompany its growth. When magma forces its way into new rock, it fractures that rock, producing distinctive earthquake swarms. In recent months, instruments in the region have recorded an uptick in low-frequency seismic tremors northeast of Mount St Helens. These tremors are not the sharp jolts associated with tectonic faults, but the kind of long-duration vibrations that occur when magma and hot fluids move underground. Their pattern matches the migration of the plume, providing another layer of confirmation for the subsurface imaging results. Geophysical models suggest that the plume's current expansion zone lies between 6 and 12 miles beneath the surface, a depth at which rock is hot enough to deform plastically but still solid in many places. As magma moves into these layers, it melts surrounding rock, enlarges its own conduits, and changes the thermal structure of the crust. Over time, this can weaken overlying formations, making them more susceptible to uplift, fracturing, and, eventually, surface expression in the form of new vents or lava domes. While such changes may take years or decades to manifest, the mere fact that the process is actively underway speaks to the dynamism of this volcanic system. One of the most intriguing aspects of this discovery is its potential to connect with older volcanic features in the area. To the northeast of Mount St Helens lie smaller volcanic edifices and ancient lava flows from eruptions that occurred thousands to tens of thousands of years ago. It is possible that the new plume is moving towards structural weaknesses that date back to those earlier events. If so, it could tap into a region of the crust already conditioned for volcanic activity. Such a scenario might mean that what is happening beneath Mount St Helens today is part of a longer cycle of shifting magma pathways that periodically redirect volcanic focus within the broader Cascade arc. Temperature measurements taken indirectly through electromagnetic surveys indicate that the plume is not only growing in spatial extent, but also increasing in thermal intensity. The hotter the plume, the greater its ability to melt surrounding rock, accelerate upward movement, and potentially merge with shallower magma bodies. An important point to remember is that magma plumes do not simply vanish. They either cool and solidify underground or continue to feed volcanic activity until pressure is relieved. In the case of this secondary plume, there is no indication yet of cooling. Instead, all signs point toward sustained energy and movement. From a purely geological standpoint, the northeastward expansion could also alter the stress field around Mount St Helens. Magma injection changes how the surrounding crust bears weight, which can, in turn, influence nearby faults. The Cascades are seismically active not only because of volcanic processes, but also because of tectonic forces, and the two systems can interact in subtle ways. An expanding plume could redistribute stress in a way that triggers small earthquakes or changes the pattern of regional fault movement. Even without producing surface eruptions, such changes would be a powerful reminder that the land here is part of a living, shifting geological framework. The technology used to monitor this development is a triumph of modern geoscience. Decades ago, such a plume could only have been inferred indirectly through sparse earthquake data. Now, an array of broadband seismometers, ground deformation GPS units, gas emission sensors, and aerial remote sensing platforms make it possible to visualize the underground architecture with remarkable clarity. This has allowed scientists not only to detect the plume, but to observe its evolution in near real time. The patterns emerging from the data hint at a sustained source of magma feeding the system from depth, with the plume acting as a high-efficiency delivery channel toward the northeast corridor of the volcano's geological footprint. Understanding why the plume has taken this particular path requires considering both geological history and present-day crustal conditions. The northeast flank of Mount St Helens is marked by a network of fractures and past debris avalanche deposits. These features may offer lower resistance to magma migration compared to the denser, more intact rock in other directions. Additionally, gravitational studies have shown subtle density anomalies in this sector, possibly remnants of older intrusive bodies. Magma is more likely to intrude into such zones because the surrounding rock has already been thermally and structurally altered. In effect, the plume may be exploiting a preconditioned corridor carved out by the region's volcanic past. For the scientific community, this unfolding event represents an invaluable opportunity to study plume dynamics in a continental arc setting. While mantle plumes like the one beneath Hawaii have been extensively studied, secondary plumes associated with subduction zone volcanoes are less understood. Here, the interaction of subducted materials, mantle melts, and crustal structures creates a complex, multi-level magma supply system. Observing a plume's initiation, growth, and directional shift in such a setting could yield insights into how these systems evolve over centuries and how magma plumbing networks adapt to changing pressures and stresses. The plume's growth northeastward could also have implications for regional geothermal activity. Rising magma heats surrounding groundwater, creating hydrothermal systems that can extend well beyond the main volcanic edifice. As the plume expands, it may begin to interact with aquifers and fault zones in the northeast sector, increasing the potential for new hot springs, fumaroles, or steam venting in areas that have not exhibited such activity in modern times. Even minor changes in surface heat flow could be significant indicators of the plume's influence reaching higher crustal levels. Geologists are particularly interested in how the chemistry of erupted materials might change if magma from this secondary plume eventually reaches the surface. Different portions of the crust impart distinct chemical signatures to magma as it passes through. If the plume rises through older volcanic deposits or different types of country rock than the main chamber, any future eruptions it feeds could have noticeably different mineralogy and gas composition. Tracking these changes in real time would give researchers a direct link between subsurface magma pathways and surface eruptive products, something rarely observed with such clarity. The monitoring effort is being coordinated across multiple institutions, combining resources from universities, government geological surveys, and international research groups. This collaborative approach is vital, as understanding a moving magma plume requires integrating many types of data, from seismic velocities to ground tilt measurements, to variations in magnetic field strength. The more comprehensive the data set, the better scientists can model not just where the plume is now, but where it is likely to go next. Early modeling attempts already suggest that the northeastward trend is not a brief anomaly, but part of a sustained migration that could continue for years. Given Mount St Helens' well-documented history, there is a deep awareness of how rapidly conditions can change once magma finds an efficient path upward. For now, the activity remains well below the threshold of any direct surface impact, but the scientific significance lies in catching the process in mid-course. Most of the time, geologists infer past plume activity from the rock record long after the fact. Here, they are watching it unfold live, capturing each step of the plume's development, and using that knowledge to refine theories about how magma systems behave in active arcs. The northeastward expansion also brings into focus the interconnectedness of the Cascade volcanic chain. Volcanoes are often studied individually, but beneath the surface they may share deeper sources of magma, especially in closely spaced regions. It is conceivable that changes beneath Mount St Helens could influence or be influenced by deeper processes feeding other volcanic centers in the range. The recognition of a secondary plume provides a new piece in this complex puzzle, suggesting that the magma plumbing system may be more branched and dynamic than previously assumed. As the weeks and months progress, the monitoring network will continue to feed in high-resolution data, allowing geologists to refine the 3D models of the plume. Already, the images suggest a plume head that is broadening laterally while maintaining a strong thermal gradient, an indication that fresh magma is still ascending from depth to replenish it. The balance between lateral spread and upward movement will be a key factor in determining whether the plume eventually contributes to surface activity or remains a deep-seated feature that slowly dissipates heat into the surrounding crust. The broader implication of this discovery lies in the reminder that volcanic systems are rarely static. Even in periods of apparent dormancy, they can reorganize internally, redirecting magma, altering stress fields, and setting the stage for future events. The secondary magma plume northeast of Mount St Helens is a tangible expression of this hidden dynamism, a living channel of molten rock reshaping the deep architecture of the Cascade Range. For geologists, the chance to study it in such detail is not just a matter of local importance. It contributes to the global understanding of how subduction zone volcanoes evolve and how magma systems adapt to the shifting patterns of the Earth's interior. This is a moment when the science of volcanology intersects with the raw forces of the natural world in real time. The ground beneath the northeastern flanks of Mount St Helens is telling a story that began millions of years ago and is now entering a new chapter. With each seismic tremor, each fractional shift in the crust, and each heat anomaly detected deep underground, the details of that chapter come into sharper focus. The plume's journey is ongoing, and for now, its expansion continues, an active, unfolding process that draws the eyes of scientists and reminds anyone who looks closely that the Cascade volcanoes remain, at their core, very much alive. The growth of the secondary magma plume northeast of Mount St Helens is not only a structural phenomenon beneath the crust, but also an evolving thermodynamic process that reveals much about the deep forces shaping this region. Each step of its migration and expansion follows a complex interplay of buoyancy, pressure gradients, and rock composition. As molten material rises from its source, Its density relative to surrounding rock determines how quickly it moves and in which directions it can spread. In the case of this plume, geologists believe the molten mass is slightly hotter and less dense than the crustal layers it penetrates, giving it enough buoyant force to push through solid rock, but not so much that it pierces upward at a steep angle. Instead, its energy is channeling along a gently sloping northeast trajectory, steadily carving new subterranean passageways. Deep in the crust, molten rock rarely travels in perfect cylinders. It tends to widen, branch, and sometimes pool in temporary storage zones before pushing forward again. The secondary plume northeast of Mount St Helens appears to have already formed at least one such staging area, a bulbous reservoir where magma has slowed and accumulated before continuing its advance. This pause and push dynamic is significant because it changes the pressure distribution underground. The more magma gathers in these intermediate chambers, the greater the potential for sudden surges, when pathways open and the molten material drains into new fractures ahead. Mapping these reservoirs has become one of the main focuses for researchers, as they are key checkpoints in the plume's evolution. The chemical makeup of the plume's magma is another dimension of study. Samples can't be directly collected from such depths, but geologists use indirect methods such as measuring the speed of seismic waves passing through the plume zone. The travel time of these waves changes depending on the temperature and composition of the rock they move through. Early analyses suggest that the magma in this plume may have a slightly different silica content than the magma historically stored beneath Mount St Helens' central chamber. A variation like this can mean the plume's source taps a part of the deeper melt zone enriched with different minerals, which could in turn affect the viscosity and gas content of the magma if it rises to shallower levels. An aspect gaining increasing attention is the role of volatiles, water vapor, carbon dioxide, sulfur gases within the plume. As magma rises, the reduction in pressure allows these volatiles to come out of solution, forming bubbles that dramatically increase the volume of the melt. Even without any eruptive activity, volatile-rich magma can alter underground pressure regimes and create pockets of intense gas buildup. Geophysical sensors in the northeast sector have begun detecting minor but consistent increases in diffuse soil gas emissions, a subtle sign that deep gas release is already occurring along fractures connected to the plume. The northeastward path also intersects with a set of deep crustal lineaments identified in previous structural surveys. These lineaments, which are essentially ancient fault-like zones of weakness, may be acting as guides for the plume's motion. Such structures are remnants of older tectonic episodes, possibly predating the modern Cascade subduction system, and they remain susceptible to reactivation under new stress or heat conditions. When magma encounters these zones, the reduced mechanical strength of the rock makes intrusion easier, accelerating the plume's migration compared to surrounding areas. An intriguing hypothesis emerging from current models is that the plume's movement could influence the development of a secondary volcanic center entirely separate from Mount St Helens' main cone. This would not be unprecedented. Volcanic arcs sometimes produce satellite cones or fissure-fed eruptions at considerable distances from their primary vents. In this case, if the plume continues its northeast trajectory and maintains a steady magma supply, it might eventually reach a zone where the overlying rock is thin enough or fractured enough to allow magma to ascend rapidly. Such a scenario would mark a significant shift in the volcanic geography of the region. Geodesists monitoring ground deformation have noted minuscule but consistent patterns of uplift in a broad area northeast of the mountain. These movements are far too small to be perceptible without precision instruments, but they match the modeled footprint of the expanding plume at depth. Uplift of this kind occurs when magma accumulates in the crust, displacing rock above it. While still in its early stages, the deformation pattern is considered a hallmark indicator that the subsurface processes are exerting mechanical influence on the surface landscape even without eruptive activity. The interaction between the plume and surrounding hydrothermal systems may also set off a chain of changes in subsurface fluid circulation. Hot magma acts as a heat source for groundwater, creating convection systems that can transport heat and dissolved minerals toward the surface. This can alter the chemistry of existing springs, and potentially create new thermal features over time. Researchers are closely watching for shifts in temperature or composition in springs within a 20-mile radius of the northeast flank, as even small variations can reveal changes in heat flow patterns caused by the plume's advance. In the wider context of subduction zone volcanism, the detection of such a secondary plume is a reminder that volcanic plumbing systems are rarely as simple as a single vertical conduit. Instead, they function more like networks of arterial channels, with branches feeding different parts of the crust. The migration of this plume may be part of a cyclical redistribution of magma, where energy alternates between multiple outlets over decades or centuries. These cycles are difficult to document because of the slow pace of change, but the current observations offer a rare real-time view into one phase of such a cycle. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the magma plume's impact? What do you expect next? We want to hear from you. Thank you for watching, and see you next time.